家午安。那我们今天的话，首先会提到水晶结构。在1982年，普菲特丹旭的们他利用穿透式电子显微镜，发现水晶。在他的相关实验室当中，我们也他也记录了水晶结构时空对称。那等一下的话，我们其实会使用体验来证明这个水晶结构确实是存在的。那我们事先其实有把水晶结构放在穿透式电子显微镜里面，所以我们现在就来示范一次。
上页。
那这个的话，当初菲特的学生们，他其实就利用类似的穿透式电子显微镜，早期的穿透式电子显微镜，去发现这种无重对称的影像。那也其实也获得了相对应的时重对称的绕射图案。那我们已经把标准那个累积的试片放在 T 验里面试，T 验的仪器里面，所以我们现在就来示范一次哦。
先 image。OK。
这是累积水晶试片放在 T 验里面的微小的区域去放大的。那这个是水晶结构啊，可是它其实没有像我们刚刚看到那么漂亮的无重对称。所以我们就用绕射图案去证明这个是时重对称的一个结构。所以我们现在把它切换到绕射模式去嘛，用传统式电子显微镜把它切换到绕射模式去。所以我们确认刚刚的那个试片的话，那个影像。这个影像的话，其实我们可以看到，它其实是时重对称的。时重对称的一个晶体结构。所以这个其实是有1、2、3、4、5、6、7、8、9、10个对称的一个绕射点。所以这个是当时的薛德门教授他首先第一个公布出来的，推翻了早期的结晶学的一个概论。那现在我们就请那个 Professor 那学者们来给我们一些建议。
So I guess maybe you can share with us how you feel when you first see this tenfold symmetry and describe to us what you're feeling at that time.
Okay.
Maybe go back to that memory.
Yeah. My Mandarin is not very good, so I will speak English.
他中文不是很好，所以他讲英文。
So when I saw this picture,
他看到照片的时候
then I counted them. I said, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh no, no, no. 3, 4, 5, 6, 7, 8, 10.
哦，没有。
Then I wrote.
看上一页，PowerPoint 上一页，PowerPoint 上一页。
Look here.
There you go.
No. Yeah, but you want to see both. Look here, picture here. This is exactly what I had right there. I counted them. I said tenfold, and I wrote tenfold with 3 question marks.
他看到有10个点，10重对称的点，他非常的惊讶，所以他在他的那个时间记录簿上面特别画了3个问号，所以那3个问号非常的重要。
Then I said, okay, this must be twinned crystals. Maybe Peng, you can explain in a few words what are twin crystals.
他认为这可能是一种双晶啊，所谓双晶是2个很像，就像双胞胎一样的2个晶体，可是它是互相对称的。啊，在材料里面它确实是有点像的，可是他刚开始认为这样，但后来
Which means the polycrystalline materials with very small crystals, but they are twin related. Okay? This is what I thought. And I said to myself, okay, I will try to find the twins. And then forget it.
好，他本来想说这应该是那个双晶，可是他怎么找，他就是找不到，他就是不认为这个真的是，就是没有办法证明它是一个双晶。
And so what you see here, this is a series. You see all these connections. This means that it was all working on one brain. All these links means one brain. Here, different brain. This means all this is one brain. And all these experiments are dark field experiments to find the twins. And then what they did, and these are the experiments. This is a plate number 1727. So 1727 is this. And this is a partial drawing of that, just that. See that? Right here. And then I took dark field images from here, and from here, and from here, and so on. And if one of them, of this spot, would result from one twin, then I would see only one twin in the dark field. But everywhere I saw the whole brain. There were no twins with the resolution of that microscope. That microscope was a Philips 400 microscope. This is a Joel machine, the other one was a Philips machine.
Explain a little bit. 他原来认为如果是双晶的话，它会有好几个晶体。那好几个晶体的时候，这里面的这些点会属于几个晶体。啊，结果他就是利用这每一个点呢，下去做出一些暗场的照片。所谓暗场照片，就是看看这个点出来的那个晶体在位置在哪里。啊，那结果他发现这所有的点都是从同一颗晶体来，不是2个晶体，不是所谓的双晶。所以因此他这样子认为，他找不到双晶，而且他利用了这条线，代表他就是找到同一颗晶里，一直在同一颗晶里面找，就是找不到双晶。所以似乎不是这个东西就不是双晶，而是他后来称的叫准晶。
Okay, so no twins. Okay, I said, well, maybe the resolution of the microscope is not high enough. And then I performed another experiment. This is another experiment right here. This is called micro-diffraction experiment, or CBED, convergent beam electron diffraction, CBED. And in this experiment, you converge the beam, the electron beam of the microscope, to a very small spot. That spot on that microscope was 40 nanometers. Modern microscope is smaller, but then it was 40 nanometers. So if I had twins that are as small as 40 nanometers, then I should hit one twin and then look at the diffraction pattern. So I took all these micro diffraction patterns, but anywhere I look under the beam, you see this is the beam, I can move the specimen, and the beam is very narrow, just 40 nanometers. So this is the beam, this is the specimen, and anywhere I move, there was the same diffraction pattern, no change. It didn't break into periodic. So I knew at that time that I do not have twins in this material.
好，那接下来他因为他还是不是非常的确认，所以我们在这个材料在这 TEM 里面穿透式电子显微镜里面，我们有一种手法就是把这个电子数聚得非常非常小，这个小以前在他那个时候是14个纳米。啊，那可是目前呢，我们这个机器可以到就是这1个纳米、2纳米以下。现在的机器，这是1982年，30年前，这是现在我们是2012年，所以我们的机器现在是已经更好了啊。 在那个时候他就把它锯得很小，那试着照在就单一个经理，结果单一个经理还是得到还是得到一个绕射的图案，那表示说这个绝对不是双经，不是2个经理，绝对是一个单一的经理所获得。好，因此他自始确信这个不是双经，这是 something else， 这是其他东西，这可能就是他们最后的准经。
You must know that when somebody works on the electron microscope, there is no light in the room, not like this. Everything is very, very dark. And an electron microscopist likes to have the room extremely dark.
I agree.
Any little light like this is a disturbance. We don't want any LED in the room. We just want a screen, dim screen, and at that time we didn't have screens like that. We looked here on this screen, very dark. And so for an electron microscopist to leave the room, go out to the light and come back, electron microscopists do not like to do that. They want to stay in the dark because if you go out and come back, it takes you maybe 20 minutes until your eyes adjust again to the darkness. But let me finish. But when I saw this picture and I realized that these are more twins, I wanted to share it with somebody. And so I walked out into the light and looked in the corridor to see somebody to show it to him. And it was at NBS in the United States, in Maryland. And I looked right and left, and this is a very long corridor, maybe 70, 80 meters long. There was nobody in the corridor.
What time was that? That's at night.
It was morning. Maybe 10, 11 o'clock in the morning. Yeah. And so, nobody there. So I went back and continued to perform all these experiments. I want to tell you something regarding the time. The Nobel Prize Committee told me that my case, this prize, is probably the only discovery that can be traced to a certain date, a certain hour. So the morning of maybe 10, 11 o'clock in the morning of April 8, 1982. This was the hour of the discovery. In other discoveries, it's vague. They don't know when, what. But here, we have a firm record. This is why it is so important for any scientist to have a logbook of every experiment.
That's my
Absolutely.
OK， 那个因为我们做这个电子显微镜的人都要在非常黑暗的这个房间里面做。当他看完这个的时候他心里是非常的兴奋的。那我们通常是不喜欢出去的，因为想要把它做完。可是他兴奋到他愿意出去外面找找看旁边有没有人愿意过来看一下。结果是找不到，可是他又把这个时间写下来。那这个对他现在获得诺贝尔非常的重要。因为他几乎是最近几位这诺贝尔里面唯一有一个有时间有正确的时间，还有他的时间点有日月有时间点，所以他刚才跟所有的学生讲，这个时间记录非常的重要。好，那 I think our time is now running up. Would you like to
say a few more words?
Yes.
Okay? And then we can finish. You see, the other thing is that if you look at the diffraction pattern, there is no periodicity. Okay? The distance from here to here, if you multiply by 2, you are here. And there is nothing there. No periodicity. And if you want to understand what periodicity is, look here. Here we have a motif. This is a motif. And it is arranged in a periodic fashion. And also the motif itself is periodic. 2 periodicities. Periodicity, large periodicity, and even larger periodicity. Right? Several periodicities there. Here, no periodicity. So this is the first time that you see no periodicity in crystal.
好，这个指尖的重点就是它是没有那个周期性，所以这边的每个点的距离是不一样，不像这个每一个点都有一点距离。好，那这个我们在昨天的那个演讲里面稍微说明。
ST introduction. My name is Joe. I have a question. How to keep your periods in the period of the
How did I keep
your curiosity.
Curiosity?
Yes, during the period of learning.
Oh, it is a character. I am a very curious person. I was a very curious child when I was very young. I was interested in everything. I wanted to look at little details in nature, especially in nature. Flowers. I was taking apart flowers, looking inside, and collecting animals. I collected turtles. I had cats. I had rabbits. And I was very interested in details. And then one day, our nature teacher, when I was about 10 years old, there was no science at it. Nature.
Just fun.
Nature, yeah?
Yes.
He told us that there is a microscope in school. A tiny little optical black microscope. He said, oh wow, can you bring it to class? He said, yeah. And then I bugged him several weeks, and then he brought it to the class, and he said, okay, Dan, you are the most interested person, come and look at the microscope. And the whole world opened to me under this little microscope. And so this is where I really started my love for microscopy, looking at things that you cannot see with your eyes, but you can enlarge and see in a better resolution. So this is about curiosity, and I'm still very curious about everything.
Yeah.
That was primary school.
Because primary school I was about 10 years old.
10 years old. 就是他刚才有提到说，在10岁的时候呢，那个自然的老师带了一台那个显微镜到教室来。那这自然老师其实已经对他的好奇心已经非常的 impressed 了，所以他带来说就跟他讲说 Dan 这就是那个显微镜，所以他从那个时候就一直就非常有好奇心 ，even 到现在他还是对所有的事物都是非常就是说有一些好奇心，很多事情都可以引起他的好奇心。
How surprised, great the Nobel laureate, prize laureate Dr. Sherman in our classroom. Let's welcome Dr. Sherman with warmest applause. We are now discussing our physiography. We enter the topic about symmetry, especially discussing the symmetry axis. And we just enter the two-dimension. So this is 2-fold, this is 3-fold, 4-fold. And in traditional physiography, they insist that the crystal lattice must fill the whole of space, just like this. Right? This is 3-fold, they can fill the whole two-dimensional space. And also 4-fold, it's 4-fold. But with 5-fold, we find that they cannot fill the whole space with this kind of 5-fold. So 6-fold is different. Yes, so this is the code that the traditional photography is about, right? So and your discovery is important because we can fill this lattice, this small lattice with another lattice. So your crystal is combined with two lattices, right? So with two lattices combined together, we can develop the crystal with like 5-fold, even 8-fold, right? 10-fold, 12-fold. But traditional crystal they just insist that they just 2-fold, 3-fold, 4-fold, and 6-fold. So, and it's very great that you can present our question. Our next step is the student will assembling model crystal models with these tools, and they will also practice the operation of symmetry. They must have many questions to propose to you, and hope you can give us some encouragement, inspiration, or some guidance for the interest of the science. Could you please? Yes, they are a little bit.
Any questions for you since the president is here?
And they try to assemble 哪一种？像这一个结晶呢就是四次对称，我们刚刚讲到六次对称，这样这就是四次对称的一个结晶。那这个呢就是有五次对称，就是丹谢特曼博士呢他发现的这个结晶。那因为这样的结晶好像我们刚刚看的这个晶体，它里面呢就是具有两种 lattice， 就是这一个呢是这是一个菱形的，那这是另外一种菱面体，那这个两个菱面体它就组成了这个晶体，那这个晶体呢就是具有五次对称。那如果传统的结晶学呢，只有一个晶核的话呢，它只能发展出2次对称、3次对称、4次对称，还有6次对称。所以当一个晶体如果有透过2种晶核的组成的话，它就可以演绎出各种对称。那这个就是在这个化学界这是无机化学这个结晶学上面的一个伟大的一个突破。所以现在我们不只发现到有5次对称，也有包括有8次、10次、12次，甚至更多的。就有一个叫什么叫战略？
这是几年级的学生，还是研究生？
是吗？这个看起来是40个左右，但是如果我们外面是40，
all the services.
它不是两次的，这个是应该是有类似的佛法。
People live
它这个是但是这种，然后里面佛法那里面是佛法的话，佛法是怎么样？有可以讲那么多佛法就是事实学，事实学。
I see they have finished already. Yeah.
So, yeah, this is nice. So this is the 5-fold rotation symmetry here. And from here, 3-fold. Then we move from here. 2-fold. 3-fold. 3-fold again. 5-fold. 5-fold. 6 5-fold like that.
Okay, you got wanna come over here? There is a question.
And then
Yeah. So the question is that when possible we can find the crystal structure in the natural material.
Yeah. So the question is, can we find the quasi-periodic material in nature?
Yeah.
There is one paper by several scientists who did find quasi-periodic material in mineral. In a second paper, they declared that mineral is really meteorites, came from outer space. So now we have two papers on the same material. But let me tell you something, let me teach you something which is not good. These people, I asked them, when they published the first paper, I asked them to send me a little piece so that I can look at it. I wouldn't publish it, just to confirm that they have it. I said, no. We don't send it to anybody. We want to continue research. So now, there is no evidence that they are right. And this is not the way science is done. You have to be able to repeat experiments just to confirm. It's not that I don't believe them. I do. But I want confirmation. If not to me, let me send it to you, the specimen to you. If you tell me that yes, there it is, I'm happy. So science should be reproduced by other people. And if you have one specimen, now, if it is a mineral, then you can go and look for the mineral and maybe find it. If it's a meteorite, there's no chance that you will ever find the same meteorite in the world. So for the next 100 years, if they don't allow somebody to look at it, there will be one paper. That's it. So that's not science. You should allow other scientists, you should share with other scientists, you'll find it. When I published the first paper, I described exactly, you can read it, how I prepared the material. So that within 1 week, many people called me from around the world. Hey, Danny, we have it. That's fantastic. to let other people repeat your experiment, and then of course you create a community of people to work on it. Don't keep things here. Publish them, but allow other people to know what you do, explain them how to do it. This is how science works. You cannot keep one specimen in your pocket. That's not it.
我想这边稍微翻译一下哈。刚才我们这位同学问的就是说，好像目前的这个准基都是人造，他问的问题是有没有可能是用自天然生成的？那么确实有一篇文章是这样的写啊，他们认为他们是有的，可是这个材料它据说是陨石啊，就是天上掉下来的陨石，所以那个薛门呢就请他来，是不是可以提供一些样品给他们来分析一下？结果对方是不愿意啊。所以他刚才特别利用这个例子呢，告诉我们说，在这个科学上面，科学是要能够被再就是重复做这个实验。所以他在做实验的时候，每次都有很好的记录，然后呢，把他所有的这个制程都讲得非常的清楚，让所有的其他人也可以再复制，那才能造就我们这个科学的这个进步。OK。
You got questions?
Who and how does Japan crystal? How did it come up?
That's right.
Okay.
Who gives that name?
So the question is, who invented the name quasi-crystal?
Yes.
I think it's a bad name. It's not quasi-crystal, it's a crystal. It's a crystal with have a quasi-periodic structure. Okay? So, no, I did not invent it. These are crystals that obey, the mathematics behind it obey quasi-periodic equations in mathematics that existed long time ago. From the days of Fibonacci of Pisa, who published his results in the 13th century, beginning of the 13th century. Hundreds and hundreds of years ago, we know about these equations. This fits the quasi-periodic equation, and my colleague and friend, his name is Dov Levine. Dov Levine published this paper after us. He nicknamed it quasi-crystals. Now, quasi-crystals is easy to pronounce, so it catches. Rather than, I never use one. I always use quasi-periodic materials or quasi-periodic crystals. But everybody else calls them quasi-crystals, which I don't think is correct, because they're not quasi-crystals, they are crystals. Right, so Dov Levine is the name of the person to answer your question. Dov Levine.
OK。他刚才是说那个准基是怎么来的啊？那个名字 quasi-crystal 是怎么来的？其实他自己是不认为那个应该要叫做准基的，因为它就是晶体，应该是准晶体，所以他并不喜欢这个名字。可是因为有一个这个到 Living 这位学者，他发了一篇文章，然后在这里面叫它 quasi-crystal。那个篇文章只是给他一个昵称而已，结果没想到最后就变成正式的名称这样子，所以大家都叫它 quasi-crystal。现在这是这个名字。Okay.
More questions?
Hi, Dr. Checkman. We know that we have a Miller index in our traditional
Yes.
laboratory.
Yes.
So is there a new system that you created for the quantum material?
Yes. So the question is, we have, for periodic material, we have Miller indices. And so usually we have 3 Miller indices, and for the hexagonal structure, you don't see it here, for the hexagonal structure, we may have 4 indices. Yeah, this is not really hexagonal, but that's okay. So for some structures, we have 4 indices. One of the, when we published the first paper, the 3 of us, we were 4, but Professor William Black was in Israel and I was in the United States. So John Kahn and Denis Gracias and myself sat down to discuss what is needed now. And by the way, Denis Gracias is here.
Yes.
Yeah. So we said that we need 3 things. We need a strographic projection for these new materials, that means that we need new Miller indices. Not Miller indices, other indices between this carbon material. And this was one of the issues. So we invented a new system of 6 indices to describe the structure, and we sent it for publication with a strographic projection. That didn't catch, and then they can, this system is good, it works fine. But another system came up, which is more used today by other experimentalists, and also using 6 indices to describe the structure. So yes, there are new, I don't call them Miller indices because they're not Miller indices, but sort of Miller indices. They do the same thing as Miller indices do. And yeah, do they know about the strographic projection?
Yes,
they do. Okay, fine. So you understand the crystal structure, the strographic projection for every structure which is quasi-periodic. This was the first one that we published, but then they other strographic projection. Other structures.
我回去，我稍微简单讲一下啊，就刚才讲，它是有事实上可以用6个数字来代表，确实是有一个关系。
As we know, not most of the materials that will form concept crystals is metal. It's metal. Is there any ceramics formed in concept crystals?
Yeah. Well, I heard that there are polymers that arrange in a quasi-periodic array. I did not read I must admit I did not read the paper. I was just told that this paper exists. But it appeared recently, and this year I don't have time to read many papers. So I didn't read the paper, but they tell me that for polymers, there is a quasi-periodic. Anything in ceramics?
There's no ceramic.
No.
Polymer.
Polymer, yeah.
But it's only 2-dimensional polymer.
Yeah.
It's only 12 full symmetry. So the polymer, if you give a Fourier size ratio between the 2 atoms, we can get any kind of polymer. Just according to the mathematical ratio. Just imagine if you give a square and a triangle, and then if you give a right ratio, nature will have form. This is the mathematical.
Most ceramic materials have one large atom and very small atoms, and so I don't see that they can be arranged in quasi-periodic way. The ions are cations, and those with many electrons grow like this, like the oxygen becomes larger and the metal becomes smaller. So the ratios are such that I don't say that you will not find them, but I don't see how they can be arranged at this point. Because of the size difference, huge size difference.
There is one in the back. We will have some of from there.
So,
yeah.
Hi, Professor. I want to ask you a question. After a section of a new bifold symmetry, how would you like to correct the old definition of crystal? Because these are all crystals, right?
Yeah.
And would you say it's a new generation of a crystallography after this new discovery?
Yeah. You did not attend my lecture yesterday. Will you attend my lecture today?
Yeah.
I will answer that question. Because there is a new definition for a crystal. I didn't do that. The International Union of Crystallography appointed a committee to redefine crystals, and they have a very beautiful new definition. So today, if you come to my lecture, I will show you that definition.
Oh, I was there yesterday, but I didn't read, because that was their definition, not yours. I wonder whether you have a new panel.
Well, I will show it again today.
Okay, thank you very much.
We got any question from this side of group?
next mission will bring us a new generation of crystal light. And in traditional crystal, we have some point group or space group. But this new crystal, does it have a new system of space group? So, and how's the future about this crystal? And does it have some spatial general properties like hexagonal? I would say, yeah, more brittle than other.
Why are they more brittle? Why?
Because the hexagonal have more less sleep system, so they call them brittle. But does it have something spatial properties?
Yeah. No, okay, let's start from there. Well, there are, of course, special properties. I just answered one question here about these special properties and how they can be used. So let me repeat just what I said about the properties. There are certain properties that quasi-periodic material own, and these are very interesting electrical conductivity of many quasi-crystals. The conductivity goes down as you cool them down. As the temperature goes down, so does the conductivity. Just the opposite of superconductors. When you cool them down, the resistivity goes to zero. Here the conductivity goes to a very low value. There is a low heat conductivity. They have interesting catalytic properties, and Anton Tsai is an expert on that. You can use powders, and you can use the atoms on the surface, which are very stable, to use as catalysts in the copper and so on. And then there are other properties that are hard, but they are hard like every other intermetallic compound. They are brittle, just like most intermetallic compounds. Not all intermetallic compounds are brittle. There is at least one branch of intermetallics with the structure B2, which are ductile, extremely ductile. But quasi-periodic materials are usually brittle. Dislocation move there, but it's not easy to move them at room temperature. At high temperature, they are ductile, like most metallic intermetallic. So these are some of the properties that can be, and some of them can be applied, find some applications, and even try to do that, like the low surface energy for coatings, and the low heat conductivity for heat transfer prevention. That means like insulators, heat insulators, and little particles of quasi-periodic materials are embedded in stainless steel produced by a Swedish company named Sandvik, and they produce a wonderful steel, one of the best steels in the world, which is stainless steel, precipitation hardened, extremely strong, ductile, and these are used whenever. They have many uses. I don't know about all these uses, but some of them. Anytime you touch metal with the human body, like in electric shavers, that the metal touches the skin, it's made of that steel. In operating room, the cutting tools, and some other materials that touch the body are made of that steel. So there are some of the potential uses and some of the real uses that already exist.
Okay, 我想那个时间差不多哈。How about let's take a group picture together? That's pretty much conclude our question Q&A session. Let's give Professor Shipman.
3、2、1。
陈老师，再照一张，把那个 poster。
好，那个人来，那个人稍微往旁边两边站一下。
那个这是上课的比较会。
正知道吗？好的，好吧。
这个那个女同学再过来一点，对。每个人都拿一下。
OK。来，旁边进来。
边，3、2、1。